Hi everyone. We're going to be talking about system sizing today for the solar charge control. For your group project, you're trying to design a system that will basically be able to help some community. There's a lot of variations for each of your goals, and that'll lead to an interesting variety of results for each of us. So the way that this is basically our focus right now up until the spring recess, and you'll notice that we have a deadline as March 27th for uploading the system sizing homework. Now this homework is not just a normal homework. This is actually helping to prepare you for the math that is necessary for your project. Basically, you're going to be going a little bit like kind of, how do you say, more thorough in this exercise compared with what you'll actually report. But that's going to ultimately be up to you. Once you develop these numbers, you're going to find what you think are the most important takeaways to report in your poster, in reporting your main results. So these slides were created in in collaboration with We Share Solar, which is the nonprofit company that makes these blue suitcases, which are ultimately used to ship to places in the world that are energy deficient, and they really benefit quite a bit from having these resources. So I'll deliver some slides and tell you about some of the concepts involved. These are available online under course materials. So if you go online here, let me just. Okay, so if you go online under course materials, you will scroll down to the bottom and you'll see system sizing materials, including this lecture slides, the handout from Hal, who is the leader of the We Share Solar, and our homework, which will be uploaded onto Blackboard. And you'll see a place underneath here where it says, well, it will say upload here. And I'll give you some more instructions in this video as well about how to do this. By the way, I'm intending that you're working with your partner on this, so you and your course project partner can submit the same form. I just do ask that you both equally contribute to doing the calculations. Ultimately, each of you are responsible for knowing how to do these calculations. So it is okay to do it collaboratively, but ultimately, please turn in your own work. Okay. What are we trying to do here? Well, we're trying to create a standalone photovoltaic system that's appropriate for the solar suitcase. And so one of the things we have to do is figure out, well, how much energy am I going to need at night? How much energy am I going to need during the day? And then we will try to figure out what system components were needed to supply specific loads for the various application contexts and locations. So you'll need to think about what that is as you're speccing out. So, by the way, everything that I'm saying here is not just to some abstract situation. It's for exactly your chosen context for your course project. So now that we've gotten that figured out, now I'm going to help guide you through for that particular situation, including its GPS coordinates and other factors. You're going to be considering those different needs and ultimately costing out the system. So in our system design, we are going to try to choose as efficient DC loads as possible. So for example, we want to choose energy efficient light bulbs as opposed to, say, incandescent light bulbs. The LED light, for example, is a 5-watt light, and I haven't had a chance to show that in class yet, but it's I would say just as bright as a regular light bulb. So these are 5 watts, and they're how can you make a light bulb that's 5 watts, but it's just as bright as a 60-watt light bulb? Well, it's because that the traditional incandescent bulbs are not just producing light, but they're also producing a bunch of heat as well. And so whereas the LEDs do not produce as much heat, they produce some still, but they're producing mostly just light. So we're going to determine our system voltage. Generally, solar suitcase is a 12-volt system. For those of you working with a bigger scale, you might ultimately consider whether it might be more appropriate to have multiple charge controllers sort of broken up into smaller pieces rather than having one huge photovoltaic grid, in which case the cost is going to increase, but you might try to think about where is that balance point? What's the balance of all those parameters? There will be batteries involved. These will basically be lead acid batteries, which are the cheapest ones. And when you're looking for costs, I would recommend just going to the internet and just type in, lead acid battery or car battery or something like this. You need to figure out what the costs of these are and what the amp hours are, or if I'll refresh your memory about the watt hours, you can convert between the two. So batteries, why do we need batteries? Because if the solar panels are working during the day, let's say you need some of that energy at night, then you're going to have to wait till the next day if you don't have a battery. So the battery is a way to store that energy. Maybe you didn't use all the energy that was being produced during the day, and you can use some of it at night. So these photovoltaic panels will be used to supply both daytime and nighttime loads. And lastly, we're going to be considering what kind of charge controller we need, and we'll basically decide based on how many load amps that we'll need, basically, for our given system voltage. Okay, so we've got a car battery here or so, and we're thinking about different types of loads, right? So a 6-watt LED, 3-watt LED, maybe 5 watts to charge up an e-reader, or maybe even your phone, and then more if you wanted to actually charge like a laptop computer. Generally requires 40 watts. I'm just looking right now at my laptop charger, and in fact, I'm going to bring this onto the camera here actually, so because I do have a camera here, and we'll make use of this from time to time, and you can see here it says Dell. 90 watts. So like up to 90 watts is the charging power. Now, it may be that it doesn't quite use 90 watts, but we should be ready for that nonetheless. Okay, so those are some of the kind of considerations of the loads. In your activity, as you'll see in the worksheet that's attached on Blackboard, you're going to need to brainstorm and come up with what are the key things that you think are going to be necessary to satisfy the community or person or people that are involved in your project. So you're going to be thinking about things about, well, how many hours will my lights and computers be working or being on? How many batteries and how many solar panels do I actually need, right? So you'll need to be thinking about these kinds of things, and you might have to do a little trial and error and think, well, I don't know, I mean, maybe it's that if it's a classroom type of setting, maybe we need to have a few laptops, right? Or maybe maybe we can get by with just charging phones for part of things, right? So those will be some considerations that you should really spend some time thinking about. Ultimately, when you're presenting your posters, you'll need to justify the choices that you made to your audience. They'll be curious, well, how did you determine that there was 3 laptops in this building? And you can answer based on the context of what you projected that the needs would be for that population of people. So here's the big pictures. We've got these solar panels. They're charging up a battery, and then that battery is ultimately then going to your loads or your appliances, right? So you have energy that's stored in the battery. If there's moments where the battery is totally charged up, then the solar panels can just be used to go directly towards these other things. So that's kind of our picture of the generation side, the storage, and then the consumption side. Um, we're going to need to be thinking about daytime and nighttime loads separately. Why? Because the isn't it all just energy? Well, the nighttime is going to depend on that energy being able to be stored by a battery. Um, and so we'll need to be thinking about the number of hours of sunlight at your location, maybe some seasonal variations, especially if you're, kind of far away from the equator, and and then the context. If it's, for example, a health facility where it's absolutely urgent that there is constant availability, or if it's something like for leisure time. So if it's if it's to provide maybe a family with some place to relax and read after work, is it perhaps not a life and death issue if the power does go out from time to time? So there's some things that you might think about in your specifications, what you're considering. So nighttime loads, what are they? They are supplied by the battery. So I'm generally thinking about lights, right? Lights are going to be really helpful at night in any part of the world. If you don't have access to electricity, then having some energy stored in a battery, which can even just provide a little bit of light, will help improve the quality of life. What are daytime loads? Well, daytime loads basically are things that you can make use of the sunlight energy directly without having to really store it in a battery. So things that you can actually charge, like e-readers, your headlamp, a phone. Wow, this is such an ancient picture of a phone, right? And any other devices that you can think of. Then we don't need to waste money buying a larger battery if we can just charge those things during the day. So in other words, you have to tell the end user, you can't charge your phone at night. You need to charge it during the day because that's the way that we've specified for our system. We didn't want to have to buy a bunch of extra batteries for our project just so that people can have the convenience of charging their phones at night. So really phones and stuff and headlamps, etc., those should be charged during the day, given this way of thinking about things. Okay, so you're going to be creating a table that looks sort of like this, right? So it could be an activity or it could be a device, and you're trying to think about, all right, well, so the lighting is 5 watts, let's say, right? An LED light. How many hours per day am I going to need this? Based on that, remember it's the watt times the hours, like is shown in here in these last 2 rows here. The watts times the hours will give you the energy in watt hours for the day that is needed. Now, you might have to justify, is this going to be a daytime or a nighttime kind of thing, right? So you might have to think about, is this going to be, maybe it might be some of each, right? In which case that you might say, well, this is 120 watt hours, but 80 of it's going to be during the day and 40 of it will be at night. It's just unavoidable, and you might justify why that is, right? Also notice that the newest iPhone is spec'd at about 12 watt hours is kind of its daily usage, basically, or sorry, that the amount that it would take to charge it up. So this idea here of 5 watts charging for 2 hours per day, that's probably about right. So that's how much you might expect 10 watt hours or so for charging up a phone. That's about right. How much energy is needed to supply nighttime loads, sorry. So if you had an outdoor light, that's on maybe for 3 hours. So maybe then you can imagine a classroom light. Maybe you have classes running at night. You have another classroom that's running. And then maybe you have a dormitory, right? And maybe this is going to be, on for, let's say, 5 or 6 hours in the evening, and then maybe for the first 2 hours of the morning, maybe from 6 a.m. for breakfast time or something like this, right? So how many watt hours then in the total battery capacity are needed to satisfy or to supply these nighttime loads? Well, what we need to do is we need to say, okay, well, we'll take the first one, the 6 times 3 hours, so that's this one here, plus 2 of these ones of the classroom lights. Let's imagine that we have 2 classroom lights, and each one is 5 hours times 6 watts. So in other words, that's 30 watt hours, but we're multiplying this by 2 because we have 2 of these classroom lights. And then we have 3 watts times 10 hours for the dormitory. So you add up all those numbers together, 18, 60, and 30, and you get 108 watt hours. That's our nighttime loads that we'll need for this example. Okay? So photovoltaic or PV panels are rated in watts and volts. And so we're going to assume that we're using panels for a 12-volt system, and the more hours of sunlight received, then the less PV capacity or watts you need. So let's work out a couple of examples here. How much energy does a 100-watt PV panel generate with 3 hours of full sunlight? And how much energy does a 100-watt PV panel generate in 6 hours of full sunlight? So let's work both of those situations out here. So let me just write down the numbers here, and then we can kind of take it from there. So a 100-watt panel, and then this case 1 was 3 hours of sunlight, and case 2 was 6 hours of sunlight. Okay, very good. So if we take these 2 numbers here, we can say, all right, well, I know that if I have 3 hours and I'm producing energy at a rate of 100 watts, then that's going to be 300 watt hours that's being produced. So in 3 hours, so remember that nighttime load situation that we looked at a moment ago, that was 108 watt hours. This 300 watt hours already exceeds what we need, right? If we took the same 100 watts and we had 6 hours of full sunlight, then we could say that we had 600 watt hours, which is definitely well beyond what we would need for the nighttime loads. But we didn't calculate the daytime loads yet. Okay, so something weird happened here with this. Let me just pause here to. That's very strange. Okay, just a moment, please. It was working just a second ago, and then now it stopped working. So, okay, so we're back here. All right, so we're back, and it looks like everything is working okay now. So, here's the thing. The sun is not out all the time. I mean, maybe that's obvious, but the thing is that, like, what do we mean when we say that there's 6 hours of sunlight? Do we mean 6 hours that the sun is right up overhead? Because we know that's not true. Maybe, maybe some of the time it's going to be behind the clouds, and then some of the time it's actually totally cloudy, right? And so when we put in all those things in here, we basically have to think about, well, how many like equivalent sun hours are there? And so part of our system sizing worksheet, which you will see in just a moment, is designed to try and help us consider how many basically solar hours or sun hours that we have in our given location. So the way that we calculate it looks something like this. In Hayward, you would look up either hotspotenergy.com or the National Renewable Energy Labs PV watts calculator. We'll go there in just a moment. And you can look up, okay, the solar time, this is the time of day, like 4 a.m., 5 a.m., 6 a.m., etc., up to 6 p.m. And you can see that this is how many watts per square meter. Well, in the middle of the night, there's not really that much, right? Maybe it's like still like a little tiny bit, but it's not very much. And then it gets bigger and bigger and bigger and bigger. And then you can see here that it gets smaller again, right? And then the watt hours per meter is just multiplying by 1 hour for each of those. So if you added all those up together, you actually get the total amount of watt hours per square meter in a day. And so you probably remember that 1 kilowatt per square meter was what we sort of estimated as the sun is delivering this sort of exact number. Now we also have qualified, well, maybe that's not exactly true, but this gives us a more accurate read on things. We say, okay, well, we had 7.6 kilowatts hours per square meter per day. And so we just basically call this as 7.67 sun hours. And so this is the PHYS calculator, which also, let me just bring up, this is our system sizing homework here. By the way, notice that you'll put your name over here. And I know it's a little bit of a task, but you're going to put all of your work in green font. How do you find green font? Well, when you start putting in some solutions here, you can see that it's already in green for some of these things. And if not, you can always go up here and then select some color of green. I actually don't care if you want a darker green, that's okay. But it will very much help me to find where your work is. The PHYS calculator is here. You can hit Control, click on it, and we see that the PHYS in-rail calculator shows up. So if we type in Hayward, California, we can hit Go, and then this website is going to find our latitude and longitude. And here we are. That looks like the right place. And we'll say Go to System Info. And the worksheet will ask you to do a couple of things, such as turn this tilt degrees angles to 0, and then go to the PHYS result. Now, when we do this, we actually get the amount of solar radiation. And so you can see that probably the 7.68 or so, or maybe it was June or maybe it was July, was the time that this person made this calculation here, is the 7.6, right? So the 7.6, so this was for the month of July, it looks like. I'm sorry, I don't know, it looks like it was June, but okay, we're pretty close, right? And so anyway, you're going to be working with that to figure out the number of sun hours that you have. So that's like, basically it's like saying if this is let's just say it's 8 sun hours, that says that a day is as if the sun was up above, directly above, for 8 hours, right? So it's taking all the complexity of the sun is rising, yeah, it's going behind the clouds sometimes, but sometimes not. And so we're reducing that all down into one number. Every day is as if the sun just hovered directly above for 8 hours, right? In this particular case. In your case, it may be different. So this is the equivalent number of hours it would take to deliver the observed amount of solar energy if the sun was always shone, if the sun always shone, not sure if that's even the right thing, with an intensity of 1 kilowatt per square meter. Okay, so if you know the number of sun hours per day and you know the photovoltaic capacity, well, you can determine or calculate the watt hours of the panel that will generate in a day. So location definitely has a big part in determining the sun hours per day, but the context also is determining the sun hours that you design for. Some things you might need to think about is, for example, does the number of sun hours vary significantly over the year? So if you live in a very high latitude, such as Alaska, this is going to make a big difference, right? During the summer, it's going to be a lot more sun hours than in the winter. Whereas if you live near the equator, it may be kind of robust. It might be around 5 sun hours every day. It doesn't matter about the seasons as much. Is power availability essential for all times? And do you need to plan for the worst times? For example, is there some healthcare needs? Or what if there is some war? What if there's something very serious that really needs the electricity, right? So these are things to consider in your design. This website, which is also linked to in your worksheet on system sizing, has some really good maps that show sun hours for different regions of the world. So the redder it is, basically, then the more the more sun there is at that location. So you can see like kind of Arizona, Southern California. Like this is kind of like the best place that you would put solar panels, right? Kind of some of the worst places would be somewhere up here in the Northeast or Wisconsin, for example. Okay, so let's do a system sizing example. This is going to help you to actually do it for real for your homework, which is ultimately contributing to your course project. So here's what we need to do. We need to sum up the energy consumption for all the nighttime loads. So we're also going to multiply by 2. And you say, well, why 2? Well, it's to account for the fact that the battery discharge depth, that means that we don't want to bring the battery below 50%. And so we're putting in this 2 gives us a little margin of error, basically. I'll cut to the pen and paper here for a second, just sort of have like as a symbol, if this is sort of my battery, I know this is just like a crappy picture of a car battery or something like that. If the battery is like totally full, then we basically don't want to go below 50%, right? And then once it gets to 50%, then we want to charge it back up again. Okay, so I don't know, maybe that helps you sort of think about that. So that's where that factor of 2 comes in. I've lost it. Just a second, please. Okay, there we go. Oh, goodness. Okay. All right. So that's where that comes in. So what do we do in this situation? Well, if we have 6 watts, 6 watts, 6 watts, 6 watts, that's what is that? 6 times 4 is 24 watts. And then we multiply that by 3.5 hours, we'll get 84 watt hours. And then that magical multiply by 2 for the fact that we don't want the battery to completely discharge overnight, but just get down to the 50% place. That's saying that we need to have 168 watt hours. So how many amp hours is that? Well, to do that, we need to take a watt divided by a volt is actually an amp. So you probably remember that actually from, so a watt is a volt divided by an amp. Wait a second, I think I said that wrong, sorry. A watt divided by a volt is equal to an amp. And so one way that you can remember that is if a watt is equal to an amp times a volt, that's like P is equal to I times V, right? So that's our old power equation. And so in other words, if you have something that is, let's say 168 watt hours, 168 watt hours, and you want it to be in amp hours, we can divide by the 12 volts, and a watt divided by a volt is going to be an amp. So 168 divided by 12, let's just get that on a calculator here. 168 divided by 12 is 14. So in other words, this 168 watt hours that we need divided by 12 volts is going to give us 14 amp hours is what we basically need for this situation. So that's telling us something about what kind of battery do I actually need. I need a 14 amp hour battery basically if I'm gonna have a chance to be able to keep these lights on for the time that I think it needs and still not drain the battery completely. So this is kind of, it takes a little bit of being, smart around what our needs are. Okay, now we think about the actual solar panels here. Well, the solar panels that we're going to be using here is let's see here. So basically, if I divide the number of watt hours by the number of sun hours, and then I multiply by 2, again, this is multiplying by 2. So if I didn't multiply by 2, then if I took the number of watt hours needed divided by the number of sun hours, that should be the bare minimum for how much watts I need for my solar panels. But we multiply by 2 again here because we want to take into account the fact that, well, you know what, not every day is going to be perfect, and some days are going to be a little bit worse, and some days are going to be cloudy, and we need to be ready for that. So that's why we sort of say, well, our minimum needs are going to be twice as much, or in other words, in this case, 42 watts. And this is all worked out in Hal's notes, which I guess I have here as well as paper here. So, but you can see here, for example, if you go to Hal's notes here, this is the part that we just worked out about the battery size, and there's an example calculation there. And then the solar panel size is looking at the total energy use times 2 divided by the sun hours. So in this case, well, we'll get to this example in just a second here with the 180 and the 80. So let me go back to the okay. So in this case here, the nighttime loads we calculated as 84 watt hours, but the daytime loads as 30 watt hours. Again, there's that multiplied by 2, the 15 watts from 5 and 5 and 5, and then we estimate that it's needed for 2 hours per day. And this is just a guess based on this example here. So if you think about it, then we've got 84 watt hours, and the daytime load is 30 hours. And so if we kind of put all those things together here, we can see that 84 and 30 is 114. So now if we say 114 and we do again the same thing, we say, well, we've got 4 sun hours and I'm also multiply by 2, I can see that I now need 57 watts solar panels, right? So the 42 is no longer, that we calculated from just the nighttime loads, is not enough. So we need 57 watt hours in this case. So that's how we calculate the battery needs and the solar panel needs. The last part is to figure out which kind of charge controller we need. So we need to figure out then, well, I've got my photovoltaic PV panels wattage, and we need to divide by the system voltage. And then again, we have a buffer factor, which is 25%. So 125% or 25% more, however you want to look at it, than the solar amps. And that gives you a little buffer so that we don't actually have too much current, right? So what we'll do here is we can take a look. There's different types of charge controllers that are available, and they come sometimes in 15 amps or 30 amps, etc. And so whatever value we come up with, then we basically can say we'll go with the next largest size that is available. So what I'm looking at here, when I'm looking at Hal's sheet here, is that the size of the controller, we are dealing with a 12-volt situation. So there's the 12 volts, and in an example that he came up with, he said, well, what if the solar panels that you decided on were 100 watts? Well, if you divided 100 watts by 12 volts, you're going to get something a little around 8 amps or so, and then you multiply by that extra factor here, and you get about 10.4 amps. And so they say, okay, well, we're going to choose the next available size. So you might choose the 15 amp version, or if that one's not available, you might choose the 20 amp version, so that you make sure that you can satisfy the current needs of that system. Okay, so the homework assignment, you're going to be designing a standalone solar electric system, and it's going to be for one of the communities or people that you have decided already in your project proposals. And so it may be an orphanage, a school, a community center, a refugee center. It could be a place in the United States. It could be a tiny house, for example. It could be to try and help mitigate homelessness problems, right? So there's many different avenues, as you can see, many different end goals for making use of these types of systems. And that's part of our work together, is to see the variety of those. So you're going to be specifying its location, figuring out what the lighting is, in other words, how much sunlight is available there. And there's a couple of websites that are linkable from those worksheets to help you to figure out what the lighting is. And you'll look at it in 2 different ways, actually. And you're going to be thinking about what kinds of activities are needed, in other words, how much lights, how much charging, and you're going to make estimates based on those things, what kind of loads you have. And then you need to specify what kind of solar electric components you need. So actually you're going to need to look up on Amazon or Walmart.com or whatever, what kind of battery do you need and how much is it going to cost you? The charge controllers, the cost is going to be given in these slides. And the photovoltaic panels, you're also going to have to go and probably look that up and try to figure out, well, how much does it cost for a 100-watt solar panel? you're going to have to come up with a cost. How much is this whole system going to cost? All right, so these are the things that you need to figure out. Here are some useful resources for you. Notice that there are DC appliances. This means that you can actually just run them off of 12 volts. You don't need to go and change into alternating current. You can actually just use DC directly. So for example, you can look here and see, you know, gosh, should I maybe use a DC fridge instead of an AC fridge? Would that be better in my case? What kind of lighting is available, right? So please look at these websites and see what you think would be the best for, you're looking for low energy costing appliances. So here's the summary of everything we did. If you want the size of the battery, you want to figure out what kind of size of battery you need, you should take the watts that you totally need, everything for your nighttime loads, multiply by how many hours you think you need, and then do that for every single subcomponent and add it all up together. So we did an example like that. And then when you're all done, multiply by 2. To figure out what kind of size of photovoltaic panels you need, or PV panels, you need to figure out the total number of sun hours. So that's H sun. And based on what this watt hours battery is, not just the watt hours battery, but the total watt hours, including the day and the nighttime loads, if you divide by the number of sun hours, that'll tell you what kind of wattage for your PV that you need, okay? Lastly, if you take the PV wattage and you divide by the system voltage, which in our case will be 12 volts, and you divide this by, or multiply this by 1.25, then you'll have the amperage. And as far as the charge controllers go, you should pick the next up charge controller. So here's the charge controllers here. There's some that are given, and if you look at 12 volt charge controllers, you can see that maybe there's a 10 amp version and then there's a 20 amp version. So if you had calculated that you needed a 10.4 amp charge controller, right? For this, here's an example. This is what's worked out on this worksheet here from Hal, is a daytime load of 180 watt hours and a nighttime load of 80 watt hours. And if you put all those values together, I'm going to actually go to this worksheet here so you can see it here. 180 watt hours plus 80 watt hours is 260. If you multiply by 2, that's a little over 500. And then if you divide by 5 sun hours, then that gets you about 100 watts, right? So that's how Hal had recognized that. And so then about 100 watts, that's where this one comes from here. If you take about 100 watts and then you divide by the 12 volts, divide by the 12 volts of the system and multiply by that, you know, extra breathing room factor, that's going to get you 10.4 amps. It should be what for the charge controller. But if you look at this here, you're like, ooh, well, this one's 10 amps. Should we like save some money and do the 54? Yeah, but what if you end up going in a little bit above 10 amps? Then you could break the Morningstar Sunsaver 10 amp model. So probably better to go up one thing and just pay that initial cost. So now let's do a little bit of cost analysis together. I'm going to get a new piece of paper here so we can try some cost analysis. Okay, so there's 3 questions here. How much energy will the system provide over 15 years? So one is we're trying to figure out the energy that it would provide in 15 years is the first question. And some things that I notice here is that it's 100 watts is kind of basically the average amount of power that's being produced day in and day out. So in other words, what that's basically saying is it as if the solar panel was producing 100 watts, you know, 24 hours a day. It's kind of, that's how we got there, was we looked at these solar panels and we thought, all right, well, this is a solar panel that can produce, you know, wait, I'm sorry, I just made a little mistake in the way I said that. So we were trying to produce about, what was it, 260, so this is a 100 watt panel, and we're saying that we've got, let's say, 5 sun hours, right, each day. So if we multiply those together, we're going to get it that it's 500 watt hours is being produced per day, okay? So in this case, then what we can do is we can say, well, I know that 15 years times 365 days times 500 is going to be equals to 2.7 million watt hours in 15 years. Or to give it some context here, that's 2.7 times 10 to the third kWh, right? And, you know, one thing also I'm just kind of thinking about is that, like, in California, the cost was about 16 cents per kilowatt hour, right? So if we multiplied that by 2.7 times 10 to the third, then that's $432 worth of electricity. So I hope that we're going to benefit more than $432, you know, as a result of having this thing there. Now, just even if it doesn't, you know, it's no reason to necessarily abandon the whole project, because it might sometimes cost more than, say, PG&E could do it for, you know, in supplying us, right? So there's just something to think about, is that it may cost a little bit more actually, but, you know, if this thing lasts twice as long, well, then we're going to get about, what is it, $800 something worth of electricity over 30 years. To figure out how much the system costs total, we need to think about the battery, the PV panels, and the charge controller, right? And then I'm going to add up all those things. I'm just going to give you an example right now, because I think it's better that you look these things up yourself. Let's just say that battery from Walmart costs $120, and the photovoltaics cost $80, and the charge controller was $100. Let's just say that, okay? So then that's 120 plus 80, which is 200, then 300. And then we're going to be multiplying by, it's like adding a tip, you know, at the restaurant. So I'm going to multiply by 1.15, right? So in other words, or you could say I'm going to do 0.15 times this $300. That's $45 I'm going to add on there. Or you could say I'm just going to multiply this thing by 1.15, and I've got $345 is basically like how much I'm thinking this is going to cost, right? So here's my cost, $345, and then okay, so there's the dollars, there's the kilowatt hours. So the last question asked, how much dollars does it cost per kilowatt hour? Well, that's going to be $345 per 2.7 times 10 to the third kWh. So when I put this all together, I'm going to do, oopsies, let's see here. All right, that looks better. I'm going to do 345 divided by 2.7 times 10 to the third, and it looks like the number is $0.128 per kWh, which is 12.8 cents per kWh. So it actually costs less than it would cost in the state of California to pay PG&E. Hey, what are those guys doing? They're charging us too much. All right, so I hope that you got something out of this. I hope that this makes sense to you, that it didn't just bore you into a horrible slumber where you have now drool going down your sleeve, and you would realize that it's now the end of the video. These numbers right here, where did these numbers come from? These are the ones that are given in Hal's worksheets, right? Or sorry, Hal's like system sizing thing. So what I'm talking about here is this one here, which is going to be the Hal's, you know, what is it? I forgot what it's called. Hal's handout. So this is going to be kind of the template that you're going to use to try and figure that out. But all the calculations are done in here. So for example, the battery size one with the multiplied by 2 factor, the panel size also multiplied by 2 factor, but for a totally different reason. and then the solar rating, and also multiplied by its factor, right? So those are the kind of the key things here. And you got daytime loads and nighttime loads, and you're thinking about those two different things. Now the worksheet is going to walk you through all that stuff step by step. Okay, so we've got this worksheet here. Please work through it with your partner. I want to be helpful to you. I want to like basically give you feedback as you go along, so that like it doesn't feel like this kind of daunting task where you're just like feeling lost. So I do want to encourage you to do the best that you can, put in an hour or two, and if there's places where you're getting stuck, I want you to reach out to me. I want you to say, hey, look, I'm getting a little bit stuck here. I don't know how to do this thing. And I will provide you with either more support, or I'll point you to a place in this video where I did that calculation to kind of remind you, okay, you know, that you can do it somewhat like this. But yeah, I mean, that's the basic idea. And you know, so I hope that it's fun for you, and I hope that you see this as actually like helping to bring you closer to the end goal of really completing your project. And as mentioned, the solar suitcases, we're actually going to be building those up once we get back after spring break. So, so thank you so much for paying attention. I really welcome all your questions. If you'd like, I can create a forum that's just for questions around system sizing. In fact, I'll probably just go ahead and do that. And that will be a good way for us to talk and exchange information around that. So I wish you well. Please don't forget that this system sizing activity needs to be uploaded onto Blackboard by March 27th. So that gives you some time. And what was I going to say? This should be kept as a Microsoft Word document. If you don't have Microsoft Word, you can always upload this into Google Docs, and then you can download it as a Microsoft Word document and then upload that. So that's another sort of workaround trick. But that'll allow you to fill in your numbers and your responses directly onto the worksheet. Okay. Thank you, everybody, and I hope you all are well.